this session, we will discuss Unit 2, Partial Differential Equations. The topic is Formation of Partial Differential Equations by Elimination of Arbitrary Functions. Suppose the given equation is z is f of u, let it be some equation 1, where u is a function of x by z. Now differentiating equation 1 partially with respect to x and with respect to y, we will get two more equations, and we have to eliminate the arbitrary function small f using these equations, and we have to obtain the required partial differential equation. Just we have to differentiate the given equation partially with respect to x and with respect to y. We will get two more equations, and using these three equations we have to eliminate the arbitrary function f. Form the partial DE by eliminating the arbitrary function from z is f of x square plus y square. The given equation clearly z is f of x square plus y square, where f is a function in terms of x and y. Let it be some u. Now z is f of u, clearly u is a function of xy. Now we have to differentiate the equation 1 partially with respect to x and with respect to y. Z derivative with respect to x is dou z by dou x. That is denoted with t. F of u derivative is f dash of u. Now we have to differentiate u also. Its derivative is dou u by dou x. But dou u by dou x value is x square derivative 2x, y square derivative 0. So that dou u by dou x value is 2x. Thus we will have p value is f dash of u into 2x. Let it be some equation 2. Similarly, differentiating equation 1 partially with respect to y. Dou z upon dou y. Our denotation of partial differentiation is q. Dou z by dou y is q. Now f of u derivative is f dash of u. U derivative with respect to y is dou u by dou y. So u is differentiated partially with respect to y. X square derivative 0, y square derivative 2y. Thus we will have the value of q, that is q is f dash of u into 2y. Including given equation, we will have now three equations. Now we can eliminate the arbitrary function f easily just by dividing the equation 2 and equation 3. That is a 2 by 3 gives. Clearly here f dash of u get cancelled. Now on cross multiplying, py equal to qx or py minus qx equal to 0. It is the required differential equation of first order. The required partial DE is of first order. That is py minus qx equal to 0. Form the PDE by eliminating the arbitrary function f from xyz is f of x square plus y square plus z square. Given xyz is f of x square plus y square plus z square. Suppose let it be equation 1. Now differentiating this equation 1 partially with respect to x and y. Differentiating partially with respect to x using product rule here. Yz keep it as a silent, x derivative 1. Xy is keep it as a silent, z derivative is dou z upon dou x. But dou z by dou x is p. While differentiating partially with respect to x, keep here y as constant. Now f of x square plus y square plus z square derivative, whose derivative is given by f dash, and x square plus y square plus z square derivative is 2x, y square derivative is 0, z square derivative is 2z into dou z by dou x, but dou z by dou x is p. Now taking f dash as common, we will get 2x plus 2zp into f dash. Similarly, differentiating partially with respect to y. But while differentiating partially with respect to y, keep x as constant. So here x is kept as constant, and the derivative of xyz, which is obtained by using product rule. That is xz keep it silent, y derivative is 1, and xy keep it as silent, z derivative is dou z by dou y. But what is dou z by dou y? Our denotation is q. So we will have xz plus xy cube. Now differentiating on right hand side, f derivative is f dash, x square derivative with respect to y is 0, y square derivative with respect to y is 2y, z square derivative is 2z, and then dou z upon dou y, but dou z by dou y is q, and taking f dash as common, we will have 2y plus 2z cube. Let it be some equation number 3, where p and q's are dou z upon dou x and dou z by dou y. Now to eliminate f from these equations, just we have to divide the equations. That is a 2 by 3 gives clearly f dash here get cancelled. Now on cross multiplying, we'll get the required partial dE, and simplify the equation, we'll get the required partial dE, which is of first order. Form the partial dE by eliminating the arbitrary function phi from Lx plus my plus nz is phi of x square plus y square plus z square, the given equation. So here we have to eliminate the only one arbitrary function, that is phi. For this we have to differentiate partially with respect to x and partially with respect to y. Lx derivative is L, my derivative 0, nz derivative is n into dou z by dou x, but dou z by dou x is p. Phi derivative is phi dash, x square derivative 2x, y square derivative 0, z square derivative 2z, dou z by dou x, but dou z by dou x is p. Thus we will get second equation. Similarly, doing the differentiation partially with respect to y, we will get equation 3. But don't forget, while differentiating partially with respect to y, keep x as constant. Now 2 by 3 gives the equation, and cross multiplying, we will get the required partial dE. So easily we will get the required partial differential equation just by differentiating partially with respect to x and with respect to y, and we will have two more equations. Just dividing these equations we will get the required partial differential equation just by taking the cross multiplication and simplifying the equation. We will get the required PDE. The given equation relation is phi of uv equal to 0. Now differentiating one partially with respect to x, we get phi derivative is dou phi by dou u, but u is a function of x by z. We have to differentiate u also, whose derivative is dou u upon dou x, plus dou phi by dou u into dou u by dou z into dou z by dou x. We have to give the preference for u and we have to give the preference for z also, because z is a function in terms of xy. Now differentiating phi partially with respect to x, that is dou phi by dou v into dou v by dou x plus dou phi by dou v into dou v by dou z into dou z by dou x equal to 0. This equation is written by using chain rule property. Just substituting the partial derivative values, that is dou u by dou x is 2x, dou u by dou y is dou u by dou z is 2z, and dou z by dou x is p. Our partial differentiation denotation, dou z by dou x is p, dou v by dou x, differentiating v partially with respect to x, keeping y as constant. So we will have minus 2y. Similarly, dou phi by dou v into dou v by dou z is 2z, and dou z by dou x value is p, which is equated to 0. On simplifying, we'll get the equation 2. Similarly, differentiating one partially with respect to y, we'll get one more equation, that is let it be equation 3. Now eliminating dou phi by dou u and dou phi by dou v from obtained equation 2 and equation 3. For this, just we have to take the determinant by whose coefficients x plus pz and pz minus y are the coefficients of dou phi by dou u and dou phi by dou v. Similarly, the coefficients of dou phi by dou u, dou phi by dou v coefficients in equation 3 taken in second row, and the 2 by 2 matrix determinant is calculated, which is equated to 0. Thus, we'll get the required partial DE. The partial DE is simplified so that we can get the required partial DE in general form, that is some PP plus QQ equal to R form, which is the required partial DE. So easily we can obtain the partial DE just by taking UVs and differentiating phi partially with respect to x and with respect to y. We'll get two more equations using the determinant, which is obtained by taking the coefficients of dou phi by dou u and dou phi by dou v. The determinant is equated to 0. On simplifying, we'll get the required partial DE. Another problem, form the partial DE by eliminating the arbitrary function phi from phi of y by x square plus y square plus z square is 0. Let u is some y by x and v is x square plus y square plus z square. So that the equation becomes phi of uv equal to 0. We know that the partial derivatives are here. Dou u by dou x is minus y by x square, dou u by dou y is 1 by x, dou u by dou z is 0, dou v by dou x is x square derivative 2x, remaining derivatives zeros, dou v by dou y is 2y, dou v by dou z is 2z. These are the partial derivatives which are obtained by differentiating u, v partially with respect to x, y, z. Now the elimination of dou phi by dou u and dou phi by dou v from equation 1, which gives the required partial d. For this we required the determinant, that is the determinant having dou u by dou x plus p into dou u by dou z, dou v by dou x plus p into dou v by dou z, dou u by dou y plus q into dou u by dou z, dou v by dou y plus q into dou v by dou z, which is equated to 0. Just we have to remember this determinant and we have to replace the above values, and the 2 by 2 matrix determinant is equated to 0. What is the determinant for ABCD? The 2 by 2 matrix having ABCD elements, that is AD minus BC, which is equated to 0 here. So clearly taking the determinant and which is equating to 0 and then simplifying the equation, we'll get the required partial DE. So easily we can get the partial DE just by differentiating UVs partially with respect to x, y, z's, and we have to remember this determinant and we have to replace the values, above values, and then the 2 by 2 matrix determinant we have to compute and which is equated to 0. On simplifying few steps we will get the required partial DE. Problem, form the partial DE by eliminating f from xy plus z square, x plus y plus z is 0. Given equation, let it be some u and v or expression in x, y, z's. Now the equation is clearly f of uv equal to 0. Differentiating one partially with respect to x, so we'll have this equation again by using chain rule. On simplifying the equation, we'll get this line equation. Here, dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou z values are replaced. Those are obtained by differentiating UVs partially with respect to x, y, z. Now differentiating one similarly partially with respect to y using chain rule, we will get one more equation. From these equations, we can clearly eliminate dou f by dou u and dou phi by dou v. For this, the determinant is equated to 0. Simplifying the determinant and equating to 0, the determinant of A, B, C, D, which is AD minus BC. Now determinant is equated to 0 and then simplify the equation so that we get the required PDE is in the form PP plus QQ equal to R, where PQs are first order partial derivatives. P is dou z by dou x and Q is dou z by dou y, which is the required partial DE. Now form the partial DE by eliminating the arbitrary function phi from x square plus y square plus z square ax plus by plus cz equal to 0. Clearly this equation can be written in the form that is x square plus y square plus z square is f of ax plus by plus cz. Let it be some equation 1. Now differentiating this equation partially with respect to x and with respect to y. X square derivative 2x, y square derivative 0, because we are differentiating partially with respect to x, keep y as constant. Z square derivative is 2z, dou z by dou x value is p. F derivative is f dash, ax derivative a, by derivative 0, cz derivative cp, that is a dou z by dou x is p, cp. So let it be some equation 2 and differentiating partially with respect to y, keeping x as constant. X square derivative 0, y square derivative 2y, z square derivative 2z into q. F derivative is f dash, ax derivative 0, by derivative is b, cz derivative, c constant, z derivative with respect to y is dou z by dou y, that is q, cq. Let it be some equation 2 and equation 3 respectively. Just dividing these equations will get the required partial DE. Form the PDE by eliminating the arbitrary functions f and g from the equation. Z is f of x plus ct plus g of x minus ct. So here we have to eliminate the two arbitrary functions f and g. For this we require to differentiate more than once, that is differentiating dou z by dou x, that is z is differentiated partially with respect to x, f derivative is f dash, x plus ct derivative is 1, because we are differentiating partially with respect to x, keeping t as constant. G derivative is g dash, x plus ct, x minus ct derivative is 1, minus ct derivative is 0. Similarly, z is differentiated partially with respect to t, keeping x as constant. So f derivative is f dash, x plus ct derivative is c, so that we will have c f dash. G derivative is g dash, but x derivative 0, minus ct derivative is minus c. So these are the values of dou z by dou x and dou z by dou t. Since the relations 1, 2, 3 are not sufficient to eliminate f, g, f dash and g dash, so we require second order partial derivatives. So that again differentiating dou z by dou x with respect to x. F dash plus g dash, again derivatives are f double dash plus g double dash. Similarly, dou z by dou t is again differentiated partially with respect to t. C constant f dash derivative is f double dash. Again, f double dash means x plus ct derivatives, we will have c. Already we have c into c is c square. Minus g dash into g dash derivative is g double dash, and then x minus ct derivative is minus c. Already we have minus c, minus into minus plus c into c square. Now taking c square as common, we will get c square into f double dash plus g double dash. Let it be some equation 5. From equations 4 and 5, substituting 4 in equation 5, we will get the required partial DE. So which is the required partial DE, which is of order 2. So it is the second order partial differential equation. Form the partial differential equation by eliminating the arbitrary functions f and g from the given equation, which having two functions functions f and g, we have to eliminate both the functions. For this, we require second order partial derivatives also. Differentiating one partially with respect to x and y, we'll get dou z by dou x, f of x derivative is f dash of x, e power y, keep it as silent because we are differentiating partially with respect to x, g of x derivative g dash of x, let it be some equation 2, and z derivative partially with respect to y is dou z by dou y, f of x derivative 0, e power y is derivative is e power y, g of x is here, keep it as silent because we are differentiating partially with respect to y. Now differentiating equation 2 and equation 3 again, so that is the equation 3 is again differentiated here partially with respect to y, while differentiating partially with respect to y, keeping g of x as silent, e power y derivative e power y. But what is the value of e power y into g of x? From the equation 3, we will have dou z by the notation of partial derivatives, we will have dou z by dou y is q and dou square z by dou y square is t. Thus, the equation can also be written as t minus q equal to 0. Clearly, it is a second order partial DE. So, differentiating the given equation partially with respect to x and with respect to y, and we have to differentiate one more time to eliminate the arbitrary functions f and g. Dou z by dou y is again differentiated here partially with respect to y, keeping g of x as silent, e power y derivative e power y, but e power y g of x is dou z by dou y. So using the partial differentiation notation, dou z by dou x p, dou z by dou y q, dou square z by dou x square r, dou square z by dou x dou y s, dou square z by dou y square t. So just replacing the notation, thus we will have t minus q equal to 0, which is the required partial DE is of second order. So this is the concept about elimination of arbitrary functions forming the partial DE. To eliminate the single arbitrary function, just we have to differentiate partially with respect to x and y. But the equation having two or more functions, then we have to differentiate twice or more times. Thank you.